In this video, we begin section 3.2, solving linear systems. Our goal is to develop a systematic approach for solving linear systems. To achieve this goal, we will first introduce matrices, which we do in section 3.2.1. What is a matrix? Definition 3.2.1 tells us that a matrix is a rectangular array of numbers which are called the entries or elements of the matrix. If a matrix has m rows and n columns, then its size is said to be m by n. And so this is pronounced m by n. In example 3.2.1, we want to identify the size of the following matrices. In part A, we have a matrix with 3 rows and 2 columns, which means that the size of this matrix is 3 by 2, 3 rows and 2 columns. In part B, we have a matrix with 2 rows and 5 columns. This matrix is a 2 by 5 matrix. And in part C, we have a matrix with 4 rows and 1 column. That is a 4 by 1 matrix. Next, we'll define 4 special matrices related to systems of linear equations. In definition 3.2.2, we consider the following linear system with n variables and m equations. The coefficient matrix of the linear system is the matrix containing the coefficients of the variables. The augmented matrix of the linear system is the matrix containing the coefficients of the variables and the constant terms. And we use a vertical bar to separate the coefficients from the constant terms in this augmented matrix. The matrix or vector of variables contains the variables of the system. And finally, the matrix or vector of constants contains the constant terms of each of the equations in the system. Now, we will not use the matrix of variables and the matrix of constants until later in the course in chapter 5, but we will use the coefficient matrix and the augmented matrix in chapter 3. Let's look at example 3.2.2. Consider the following system. In part A, we want to find the coefficient matrix of the system. This is the matrix containing the coefficients of the variables. Since our linear system has 3 equations, we know that the coefficient matrix will have 3 rows. In the first row of the coefficient matrix, we have the coefficients of the variables in the first equation of the system. The first equation of the system is x1 plus 3x2 minus x3 plus 4x4 equals 0. The coefficients of the variables are 1, 3, minus 1, and 4. That's the first row of the coefficient matrix. Now in the second row of the coefficient matrix, we have the coefficients of the variables in the second equation of the system, which is 4x1 minus x2 plus 7x3 equals 3. Now be careful here. The coefficient of x1 isn't 0 here. The coefficient of x1 is 4. The coefficient of x2 is -1. The coefficient of x3 is 7. And the coefficient of x4 is 0. To fill out the third row of the coefficient matrix, we look at the third equation in the linear system. The coefficient of x1 is -2. The coefficient of x2 is 3. The coefficient of x3 is 2. And the coefficient of x4 is -1. In part B, we want to find the augmented matrix of the system. And so we can take the coefficient matrix that we found in part A, 1, 3, -1, 4, 4, -1, 7, 0, -2, 3, 2, -1, and then add a column. The column of constant terms, 0, 3, and -4. These are the constant terms in each of the equations of the linear system. In example 3.2.3, we want to find the system of linear equations corresponding to two different augmented matrices. So we're given augmented matrices in this case. We want to find linear systems. Let's look at part A. We need to make a decision here. We need to choose variables. We have a lot of freedom. Now, since there are 3 columns to the left of the vertical bar, that means that we're going to need 3 variables. Let's choose x, y, and z as our 3 variables. The first row of this augmented matrix gives us the coefficients of the variables and the constant term of the first equation. So the first equation will be 1 times x. So x plus 2 times y minus 4 times z equals 8, the constant term. Second equation will be 0 times x plus 1 times y. So y minus 2 times z equals 1. And finally, the last equation will be 0 times x plus 0 times y plus 3 times z equals -9. Now we could have also chosen different variables. A common choice would actually be to choose x1, x2, and x3 as our variables. So we can also write this system of linear equations using those variables. We would get x1 plus 2x2 minus 4x3 equals 8. x2 minus 2x3 equals 1, and 3x3 equals -9. Moving on to part B, we now want to find the system of linear equations corresponding to this new augmented matrix. Again, we need to make a choice about variables. Let's again choose x, y, and z. The first row of the augmented matrix gives us the coefficients of the variables in the first equation as well as the constant term of the first equation. And so we have 1 times x plus 2y minus 4z equals 8. The second row helps us find the second equation in the system. We have -1 times x, so minus x, plus 1 times y, so plus y, minus 2 times z equals -5. And the third row gives us our third equation, 2x plus 6y minus 9z equals 9. Now notice that the system we obtained in part A can be solved quickly using back substitution, since several entries in the bottom left corner of the augmented matrix are 0. This is in fact system A. This is in fact system A, the system we solved using back substitution in example 3.1.4 in section 3.1. On the other hand, the system we obtained in part B is system B from section 3.1, which we noted could not be solved easily using only back substitution.